So here we start with the topic of today. It's the geospatial. So the geospatial, let's put it together in one definition. It's kind of an academic discipline that incorporate many fields or subjects like surveying, like cartography, also work with remote sensing, geomatics, and in general, all they use to collect, analyze, manage the data about the Earth. Even though the application of the geospatial going beyond this one. So this is what we call the cross scale here. You can see all the applications. Here it's coming from the non-geospatial industry. So that it takes us to one point that the geospatial scientists or the people who work in the geospatial, they need to be cross levels, and they should obtain too many skills, then they can understand what's the differences between those fields that might be social sciences, that might be like work on the urban planning and so on. So we can say that it's one solution in one discipline for too many subjects. So the core of the geospatial, actually so far, it's the surveying and the mapping and remote sensing, GPS and the geomatics. So in my work, actually, I'm a geomatics engineer here. Even though we can't forget actually most of the LiDAR and most of the image processing techniques, and also same as the survey techniques with the dealing with the industry that it's getting well developed here. So every subfield here, it's become like entire standalone field and applications. So we come to the machine learning then. The machine learning, it's the ability to teach the computers or the system to act like human. So this is the simple definition of the machine learning. And too many actually confused, or as you remember, there's something called 10 years challenge. They said that it was called statistics, now it's called machine learning. So what's the difference here? But the difference actually between statistics and machine learning, that statistics you are doing one process to get specific solution, but machine learning you are doing one run to teach the machine to do it again and again and again, and improve your data, improve your process to predict the data in better way. So this is the actually slight difference, because everything we study is physics or mathematics, but when it go beyond this definition, we learn that machine learning, it's the ability to teach the machine to act as human, or even go better than this. Why machine learning become so popular now? Because as you see now, the availability of the data, same as the computing methods, now we have the cloud and we have a very developed computing platforms. The algorithm so far, it gets mounted on too many languages like the Python and the R and so on. For example, here we have one package for visualization. It's on R. You can see here the health shade, how it's going like fantastic view with whatever kind of data you reflected on. So a quick view actually about the machine learning and spatial data in numbers. So if we use the capability of the Scopus analytics, we can see that since 2000 till now, we can see how it goes, the number of publications and the contributions between the ecology and machine learning, geospatial machine learning, GIS and machine learning. So we can see the trend now, it's become an active field. And specifically, it's United States and United Kingdom and China, they are leading the research so far. And most of those areas, computer science, environment, and earth sciences. Also, if you check the keywords of spatial data, and quality of life and hazard. Also, we can see the semi-train, and actually you can see it's a unique opportunity now to present or to offer too many proposals in this direction. So here, if you're not familiar with the machine learning, actually I put them in a specific way that it can be simplified in the same way that if you can learn or get something, leave message out of the seminar today. So machine learning in general, we have supervised and unsupervised learning. So we are talking here all about learning, because we say machine learning is giving the ability to the machine to learn how to process your data. So either we have supervised and supervised and unsupervised. So what's the difference now? In machine learning, usually you are dealing with, for example, let's take one example to make it easier. Let's talk about landslides. We have incidents or flooding, we have the incidents, and we have the conditioning factors that help us to understand this incident. So we have some failures. So those failures represent our target. And we have supporting variables, like you say, the digital elevation models, geological maps, and land uses and land cover. This is the variable. So in case we have the landslide data, so here we are coming to the supervised, because we have target already. Now our target, it can be categorical data or factor, we said, and it can be numerical. So in case when we have our data, it's categorical or factor based, that means it has label of names. Okay, so for example, sometimes the data that come with numbers, sometimes it's just a description kind of thing. So when it comes as a factor, we call it classification. But when it comes as number, we call regression. So in classification here, I have one case study. I'm working on it. So we have a study area in north of Iraq. I am studying the pollution of using of the PM10 in that area. So here the data that we have, it's just descriptive data. So that means it's on the scale of healthy, unhealthy, moderate, and severe condition, as you know the classification using for the PM10. So we are using this data that it's in specific area with the help of Landslide 8. We produce and using the 3 algorithms for the classification: gradient posting, naive Bayes, and random forest, to learn whether those incidents falling within which class within those images. For example, we are taking the land surface temperature and the thermal bands, and at the same time the vegetation indices. So we can see here the result of using those 3 methods, and 3 of them, they are classification. This is very important point. It gives us a prediction of the map. So we can see the X post here is giving us the best result, and we should justify why here, because of the overfitting, because of the ability of the model actually to carry on with the huge raster image here. This actually just brief before you process the data or you start with the modeling. The process actually should pass through few steps before you start the machine learning process. So usually you should categorize the problem. As we said, now you should understand that your input, it's factor, it's categorical data, or it's continuous data. And then after you understand your data, you need to match with the model that you are working on. Because some models, they're using small samples, some of them able to deal with the huge data. Also, you need to process the data. There is some missing, always there is some missing data, so you need to clean all of those aspects and transformation of the data as well. As you see now, we are working with pixel-based, with the vectors, and then you need to transfer to some packages. So you need to do with the CSV style or text file. So how you convert this and be sure that you are not losing some of the data during this transformation. So then when you find the available algorithm, you should understand the accuracy, also the complexity of the model, and the scalability, and how long does it take to run your training data. This is all of the specters you will face when you process. For example, if you deal with the KNN, the K nearest neighborhood, it might take like in one scene, within like Seoul, it will take like one night. It's just to process few training data, if you take a resolution of 30 meters, for example. So even though if you have the strongest processor or the RAM, but this is because of the loops that is done by the method itself. In the last step, you need to know how to optimize your solution. So either you compare two methods, or you fix the method itself by proposing different parameters inside this algorithm. So coming back actually to the image here. So for the regression, we have an application here. As we said, the regression, your target should be a numerical, or for example, like 0 and 1. So in the landslides, most people, they are doing the regression because they have yes or no, happened or didn't happen. So here in the study area, actually in Nepal, I did develop some methodology mixed between the supervised and unsupervised method. So as you see here, this is inventory. This is X and Y, the coordinates here, the longitude and latitude. And this is distribution of the incidents, as you see here. But as you see, it might be some relationship between those incidents because they are earthquake induced points. So I came to the clustering methods of those points, and to start to say that cluster is the best way to start to build the inventory itself. So based on this one, and using the general linear model, generalized linear model, we developed the susceptibility map, and we saw that there is some improvement when we deal with the inventory itself between the supervised and unsupervised classification. Now we have examples from the prediction and the forecasting, but let's just move on for the time being. For the cluster, now we assume that we don't have target, we don't have incidents, we are just having the variables. Okay. So in the cluster, what kind of applications that we might use? For example, if you know the unsupervised, if you work on the image processing, you know that when you have unsupervised, that means you are dealing with the images by consider some similarities between those images, or the image itself, based on the bands, based on the signature of the pixel or the colors. So in here, in this application, we have for the cluster, we have a study area in the center of Kuala Lumpur city in Malaysia. We have some air quality monitoring stations. So here they suffer from the pollution as the PM10 of 2.5. But what's the problem here? The problem is that they don't know exactly the source of the pollution. So now you are searching for the incident itself. You are searching for the source of the pollution. So here you are dealing with unsupervised classification for what? Actually, there is an algorithm used for the air monitoring. I integrated actually inside R with the pollution of this spatial component. So as you see here, there is this kind of, we call rose figure or rose plot. You can see the center here, it's the station itself. And around the station, this is the direction and wind direction. Okay, so you have the wind direction. In the wind direction, you have intensity of the pollution. So usually, sometimes you are saying north, east of this station, we can see that it's bringing extreme PM10, and then always the south of this station, it's safe. So, okay, based on this data, this is free data actually, all of the air quality stations it has. But now, when you see this intensity or this kind of high PM10 value, you have too many pollutants or too many emitters in this area, in the northeast. But how you understand which one exactly? So here, by using the cluster method, you see the cluster, we clustered this figure into almost 10 using the k-means. So we can see that during in this northeast part, we can see started to have some cluster. That means there's some intensities started to show it's as if related to each other. For example, if we take, actually this is took for 2 years, so we did like daily, hourly, and it took for also 1 year. So we started to see that there is a specific trend, it's showing all around the year, that in this area we have 3 or 4 clusters. If now we stopped, as a geomatics engineer, we stopped because the justification need some ecological and environmental scientists. So they said that, okay, the intensity of the PM10 coming from the roads, it's always getting the value of between this interval. And if it's food factory, for example, it has this value. So we started to link between those sources based on those clusters. So this also it's under the review now, this paper. So actually we got 2 papers out of this research of the machine learning with the air pollution. One more, it's about the forecasting. So in the forecasting, you see it's also supervised. That means we have our target, and it's regression, so it's numerical, and we have prediction and forecasting. Unfortunately, still there's some scientists confused between what does it mean of forecasting and prediction. So can you give me a clue now? What's the difference between forecast and prediction? Do you have any close understanding? Let's take it in based on language. In English, if you say forecast and you say I will predict, I think in English does it have too much differences?
It has difference.
Uh-huh.
Maybe the short-term prediction and long-term forecasting.
Yeah. So actually in machine learning, the prediction, it's something that always talking about either now, present, or the future. So prediction doesn't have time scale. You can predict whatever you have using the data of tomorrow or today, or for example, the entire year. You are saying that usually when this is here, this might happen. When the value of this factor getting like this landslide will happen. So always there is a relationship. It might be also old data. You can see our situation. Why always Seoul has pollution? I can predict the past, that using some data from the past, I do susceptibility map. Susceptibility map doesn't have time. It can be today, it can be last year, it can be next year. So prediction, it can be any time. Okay, I can predict what you are thinking about now. But I can forecast what will you think about later on. So forecasting, it's just about the future, that's all. There is nothing to forecast about now or before. It's just about the future. So in the forecasting, if we take an example from the USGS, when they talk about earthquakes, they don't say there will be an earthquake of 7 point something will happen after 1 year. They said there is a probability of earthquake will happen next year. So forecasting always talk about probability. There is nothing clear value about forecasting. It's just trend of time series data about the future. So this is the slight difference between them. So in case of forecasting, also our colleagues in the same study area, they wanted to forecast as well the pollution trend. But first of all, we had the chance to work on the specific actually model using the conditional bivariate probability function. Actually this method here showing that all the data analysis again using the drop on, drop out, drop in. So when we take all the data together using the pollution and the pollutants like the NO2 and SO2 and the NOx, we can see that when we drop one of them step by step, we can see the pollution start to have different relationships. So first of all, we understood that there is a different relationship between those pollutants. This is first step before we understand the forecast. And then we came to segregate this pollution. So we have like 1 to 100 scale, and we took the percentile. So every 10 value of a specific pollution, we plotted. So we started to see when we plot this pollution step by step, percentile by percentile, we start to see a specific values come up in a different way. Also, it was kind of source identification. So we can see different percentile here. It's 10 species. So you can see started to have a different direction, specifically in the first and the last. So that means that we have different pollutants around us, but they have differences in the quantity that it might be easy to identify using this. If you plot the data all together at the same time, this is small values want to go up. So at the end, we plotted the PM10 value around the year, and we forecasting just within the few months later on. So this is always we have the error scale. I see the blue zone. It's all the kind of errors, because in the forecast we need at least 10 years of data to get something significant. Move on with the landslides research. So we have like 15 minutes left. So on the landslide now, if you are interested to work on the landslides, we have the four major steps for the landslide. So we have the inventory and the landslide susceptibility map and the hazard map and the risk. So you can see most of the publication going here in the susceptibility mapping. Okay, because the risk need too many data related to the social data and the element and the risk, and also some kind of economical values that it gets from the insurance companies, and it's not available actually for the research. And also we published along all of this actually process. Start with the inventory. We have two research here using to classify the landslide inventory itself to get some significant output using some assumptions on the clustering. Also the susceptibility map. In the hazard, maybe it's a little bit interesting because it's not common. We just spot the light here on the hazard, and how can we make the landslide hazard map? In this area, actually, we call rainfall induced area. That means the rain caused the landslide. Okay, so we passed through the first step, which we prepared the inventory. Second step, we did the susceptibility map. Okay, it's already here. So in the third step, now we need to understand the threshold. The threshold of that the rain that when it can trigger the landslide. So taking this when, we need a data related to the dates of the incidents. When exactly it happened, because then we need to link it with the rainfall incidents. So we said that today it has a very heavy rain and it caused like 3 landslides. But if we don't have this data, this process is not possible. And unfortunately, in Korea, this kind of data is not available so far. And that's why you can see there is not much publication about this study. And that's my suggestion is to start actually monitor the data, and even to personal scale. So you can follow the news every day, and you have like few incidents will happen during the year, And then also you have free data from the rainfall from the meteorological department. It's free for citizens. So you can link them all together, and after 2 years you can produce some significant study actually about Korea. So after you prepare this hazard map, so you understand now where and when the landslide will happen. So if you know the where and when, you can start to integrate some land uses data, which is take from the municipality here or from anybody that it can provide you the number of residents, the amount of the industrial area, commercial areas, and the services, and you can integrate it with the result that obtained earlier and understand approximately how much losses you might face if you have one landslide happen in this specific area. So the risk, it's sometimes it's risk actually in terms of some, let's say, political issues, because they want to say that we don't have any vulnerability in this city. But we can show here if there is one landslide happened that already happened last few years and it happened again, it might cause some losses here. And we give it in terms of money as well, because this is also, it's a probability, and we give the error range. So we can come up with the, so the government or the decision makers, they should look at it carefully. Before we end up, we just want to talk about the challenges in the cross-level and cross-scaling. You can see here, there is no much awareness about what does it mean, the cross-scale and cross-level. In simple way, if we have like one field and we are dealing with the, again, because we just give example from landslides, we are dealing with the landslide data. It is just has the location without the temporal variable. So we are just having the location. And then we are using some machine learning. Let's say we are using the regression. So we are now with the same level. We are dealing with the same level. But if you start to pass, going to the hazard map, so you start to pass to another level, which is more detailed level, using the date. So you can say I'm reducing temporal and spatial results. But unfortunately, some scientists, they are dealing with in the low level just with the spatial data, and they said we produce hazard map. So you can see here this is a very big mistake between the levels. But what about the scale? The scales, actually, you can see that when we are dealing with the regression, for example, the regression or the neural, artificial neural network, also it's classification and regression method in the same time. And we are dealing with enhancing the model. Some professors or some scientists, they are bringing different model from the unsupervised, and they compare between them. Now you are dealing with the problem of level and scale together. You are crossing all the limits. This is, and then he said, this is better than this. And there is nothing like unsupervised, unsupervised, one better than each other. It depends on your data itself. But what you can do, you are working on the same scale of using the supervised method and developing the assumption within this methods. So this will bring you more conventional methods and also more conventional solutions that you can talk about. Also, we have problem with the space and place. It's also it's a new term that it's going there and here. Everybody understands the spatial data by thinking about one image. I can see forest fire. I see the fire in the forest. But the GIS is deal with the data analysis and the layers of this data. So as a GIS or the geomatics engineer, you have a different understanding with the space So you are dealing with all of those factors who are affecting the forest fire, but the normal users, they are just thinking about the place itself and thinking about the fire. So when you sit together and try to go convince some officialist like the city, municipality officialist to give you some data, they are saying that it's not needed or it's not required to do this kind of analysis because they're just thinking about the place, not the space. Also, the kind of data that is not made for the lands, for the GIS, we call surrogate data. So I am dealing with, for example, road network or the road agencies. They have their own data. It's not related to the GIS. The kind of the values, the annotations, the sort of the data, the files itself, they file it in different way, but it's not ready to be used in the GIS environment. So I need to also to understand that surrogate data always is not ready to be used directly. You should process too many things. So I recommend that in any kind of application, any research, that it's based on geospatial technology, dealing with environment or dealing with the applications, one person or one scientist from that major should be in the team, that he monitor the output and also assess the input of your work. Came to some kind of thinking out of the box. Actually, this is like a project of me that I'm trying to achieve in the online, which is called the Scientist Adoption Academy. It's kind of idea coming from the e-learning. Always you can find classes online, but you can't find the supervisor online. So this is my actually the idea that I'm working on. Hopefully it will become like something like ResearchGate, that it's deal with the supervisors, find the suitable supervisor, and the supervisor you can find the suitable students all over the world, not just limited to one institution. Thank you very much.
Thanks for long presentation. So, 혹시 질문 있으면 any question or comment?
The time actually.
Short question. So I'm really feeling that any research, including the machine learning or deep learning, is not easy. It's very difficult.
Yeah,
it's very complex.
To my experience actually, especially if you come from the engineering and not statistics background, you might afraid from some kind of laws you are doing. So you need always to go back and forth to some data scientist actually to help you about your decision to choose them, which model and what's the validation of your data.
그 산사태 하시는 분은 하자드 맵이 우리나라에 있지 않아요? 없나요? 근데 우리도 강수량을 저기 하긴 하잖아요. 근데 아직 하자드 맵은 없어요.
그렇죠.
As I know that we try to include taking into account the amount of rainfall in for the landslide hazard map, but he said we didn't yet have the hazard map.
Yes.
But there is some research for that actually. 또 질문 없어요? 네. 뭐 보시면 일단은 뭐 특정한 분야의 리서치력이 어떻게 보면은 그 데이터 사이언스 이쪽에 많이 오리엔테이션 되신 분이라 여러분들이 하는 모든 연구에 어떻게 보면 다 도움이 될 수도 있어요. 지금 마지막에 제가 이야기로는 어쨌든 훌륭한 연구가 되려면 각 분야에 사실은 또 데이터 사이언티스트가 잘못하기 쉬운 거는 그냥 잘 모르는 데이터를 가지고 막 다루면 사실은 전문성이 떨어질 수 있는데 결국은 그 다루는 데이터, 예를 들어서 랜드슬라이드라면 랜드슬라이드 전문가가 필요하고 아니면 또 여러분이 뭐 GPS라면 GPS 전문가가 그 데이터를 어떻게 다룰 건지 어떻게 구성할 거니까 사실 되게 중요하니까 서로 협력이 되게 필요하다는 걸로 전 이해를 했거든요. 여러분도 혹시라도 도움이 필요하면 한 번씩 여쭤보시면 아마 도움이 되지 않을까 싶어요. 네, 이상 박수 주시고 끝내.
About the head of the map, even though we do not have the head of the map officially, but we can adopt the other countries, the head of the map to apply to our landslide case. That means kind of the generalization of the machine learning.
You mean about the hazard itself? Actually, because you are dealing with the temporal parameter. So especially the spatial parameter, it might be get some link between the geology itself, between different countries.
And similar situation.
Yeah, for the rainfall, it's not possible as Prof. But you know that rainfall, it's related to too many factors. So you have a difference in geology, you have difference in the topology. Also, you have differences in the layer itself, or the we call it the slope material. Yeah. For example, your slopes here, you have different geological components. So some of them they have the sand, silt. So it has had different geological aspects. So it's a big deal.
Yeah, so that means the machine learning anyway we need the flexibility is very important factor to find the optimal parameters.
Yeah, that's
my
what.
feeling.
Yes, that's what we are working on exactly. So yes. Thank you. Thank you.
Could you explain one more time, because I could not understand the term you used? What was it? Cross-scale geospatial data. Did you mean scale of the resolution, like tiling of?
No, Prophets. Now actually, what we call the cross applications. Cross applications, as we saw in the first slide, we have too many applications dealing with the geospatial technology. So we have the forest fire, we have the environmental, we have the health diseases. So if you take this kind of scales and levels, so you are tracing the level to the different levels.
Is it a ground resolution level?
No.
Depending
No.
on
It's application types of cross scaling.
Oh, cross domain.
Yes, exactly.
So I think you meant cross domain. I mean.
Yeah. So this is the cross level itself. In the same time, you can focus this kind of cross scaling with the same models. So we are dealing with, as you said, the machine learning, but in the same time, we are going to the different level of data.
Okay, so what about cross level? What are you referring to when you say cross level?
Yeah, this is what we said about the data itself. For example, the
That's
data
the resolution.
No, also is not about the resolution. It is about the quality of the data.
The quality.
And the quantity. So when we said about the susceptibility map, it just deals with the location. That's all. You have some incidents happen here and here.
The amount of detail that is in the data.
Yeah, you can go for something like this. You can talk about the details. For example, in the inventory, you have like 3 or 4 attributes. You are talking Okay, for example, you are talking about just the
attribute, 5 attribute, 10 attribute.
If you go more, maybe you can go to different level.
Okay.
Yeah, something like if you come from
the
the
amount
GIS.
of detail.
Yeah, the amount of it.
Okay, thank you.
Thank you.
정보의 종류가 얼마나 네. 뭐 배운 게 좀 있어요, 저도. 이것도 지금 배웠는데. 네.
Thank you.
네. 마지막 박수 다시 하고 이제 끝내도록 하겠습니다.